Yeah, I was just looking at here and subtracting. But, you know, anytime you don't see what I did, ask me. I'll either say I made a mistake or I'll find out what's wrong. As you notice twice today, I wrote the wrong thing already. Darn calculator's too small. Okay. So, this was the case where the approximation didn't work. So far as I'm concerned, all you have to do is show me that you recognize that. You either say I want to do the quadratic equation, mess it up, you still lose the point. At least you recognize you got to do something else other than work with the first approximation. Or if you do the second approximation, and I'm not going to want you to do 20. I'm not going to give you problems where you have to do 20 approximations. The idea is you want to learn about the chemistry of here, of what's happening, what are the concentrations of equilibrium, things like that. And a lot of books don't toss this in, but I always toss this in to remind you that you always have hydrogen and hydroxide in the water, or in an aqueous solution. Okay, other questions? Yeah, I might as well do this one because I started this one the last time. The last thing we want to get to is the business with solubility products. Actually, I guess I set everything up, but I didn't get to an answer. And I pointed out that when you have this dissociate, since it's a complex ion, we're not going to worry about the problem where the complex ion itself undergoes dissociation, because later on when we come back to that section on complex ions, if you remember there was a little section at the end of that chapter that talked about the equilibrium constants for the dissociation of complex ions. And they're small numbers also, that's why that's in there. Labs out of this, we're only going to get 3 different ions. And we'll start this off again. The equilibrium expression, since this is a solid here, we only apply KSPs to things that are slightly soluble or insoluble, salts. We don't apply it to things like sodium chloride and potassium chloride because those are very soluble substances. In fact, on that list of solubility things when we're doing solubility rules, I said we'll treat slightly soluble and insoluble in the same category. They will have KSPs or solubility products. The things that are moderately soluble or sparingly soluble, even sparingly soluble, is on the borderline because that's like 0.1 molar or thereabouts. When you have something like that, you could have a KSP number for it. KSP number. Even lead 2 chloride, which says it's slightly soluble, is about 10 to the minus 5. So if you had a KSP of 10 to the minus 2, and I can't think of anything with 10 to the minus 2 for KSP, it might fit into the sparingly soluble category. So we mostly apply these things that are slightly soluble or so-called insoluble. And I pointed out there are degrees of insolubility. If your KSP is 10 to the minus 99, you get a really insoluble substance. And you see numbers like that. KSP 10 to the minus 6, 7, things like lead chloride, lead 2 chloride, there they start being, if you're not too careful, put too much water in, they will dissolve. And then you have the whole range in between that. One of the interesting things, and I haven't had people calculate this in any of the classes in a lot of years, but one of the textbooks we used to use said, if you have bismuth sulfide and the KSP is 10 to the minus 99, how many ions are in the Pacific Ocean? Okay? And when you do the calculation, they gave you a volume for the Pacific Ocean. They calculated 3 or 4 bismuth ions. And you say, fantastic. The only problem is, and when I quoted this statement, one of the textbooks I remember using said something to the effect, when this was an elementary chemistry book, but it's trying to emphasize how complex seawater is. If you take a cubic meter of seawater, you can find measurable amounts of every ion or every element in the periodic table. I don't know if that's really true, but that's what it said in that textbook. And I wouldn't believe that, because measurable amounts mean you can measure 10 to the minus 9th and 10th molar these days, so you get very low concentrations. And the reason you get such weird numbers, like saying there are 3 bismuth ions in the Pacific Ocean, we'll mention this when we get to electrochemistry. If you use electrochemical measurements to measure the cell potentials, which you can then relate to the KSP numbers, and the electrodes sense a very small distance from the surface of the electrode. In that space, they may not see any bismuth ions, they generate a high potential, and you calculate a really small number for the KSP. So that's the type of, that just says the type of experiment. You have to take some of these numbers that you see with a grain of salt, or a lot of grains of salt, I'm talking about seawater or something. Okay, so this is the first step. You always want to write the equilibrium expression, and I already pointed out to you something very important. And I emphasize product, because there's nothing in the denominator. It's a 1, because you have a solid on the left-hand side. So when you start this off, dash here, 0. And then this is sometimes referred to as the molar solubility of that compound. You can come up with a pretty small number sometimes. Then over here, and I'm not even going to write the E line because it's pretty easy. I just have to repeat what I've written here. Okay, so I'm not even going to bother it. And I got through this and I said you're set up, you're with the problem, or you come to the problem, KSP, square brackets anymore. And we already saw this was 432 x to the 7th, like that. This problem you're given KSP, you want all the concentrations. So now you divide by 432 and take the 7th root. So we do that. And you get x is equal to 1.34 times 10 to the minus 6th. Okay. And that's not the answer to the problem, though. It says what are the concentrations of each ion. And by the way, the reason it says saturated, to have a saturated solution, you have to have some of the solid present. So that just guarantees that you have equilibrium. And you recognize the saturated solution, and you start making precipitates. You see solid forming, the solution gets cloudy, all that sort of thing. So basically you're going to say something like, I guess I need some more board space here. You're going to say something like concentration of potassium ion equals the concentration of the
ion.
Because both of them are equal to 2x. And then you multiply that by 2. The biggest thing I always see mistake-wise I'll see a 10 to the minus 12. Note if you multiply this by 2, you get what? Minus 6. Okay. And I guess I can try multiplying that by 3. No, I'm not even going to do it on my calculator. I already made my quota mistakes for the day. So it's 402 times 10 to the minus 6. Okay. This is the type where you're going from K to concentration. The other type, going from concentration to K, I could say, for instance, we measured the concentration of potassium. Let's make it so I can read it. I'll read it right. What is K? Again, you can set it up exactly the same way, and now you're going to say what? Potassium is 2x. X is 1.65 and to the minus 6. Then you take that, plug it in here, raise it to the 7th power, multiply by 432. Or the other thing I can say, experiment gives .15 milligrams of zinc ion in 4.5 liters of solution. And now you have to remember you want molar solubility and all that, so you have to do 1.15 times 10 to the minus 3 grams. You look up here for zinc and you see 65.4 over 4.5 liters. And this is going to be zinc ion, which is going to be 3x, because that's what we call zinc over there. So once you get this number and divide by 3, it gives you x, and you do the same problem. Question? Along those lines, I assigned something in the homework set.
But
yeah.
I must have been with the 65.4. That's the
Atomic
weight.
weight of zinc. I looked over the periodic table.
Okay, so I can do the moles.
Yeah, in other words,
Okay.
grams over atomic weight is moles over liters molarity. Yes?
When you're doing the concentrations on top, are you plugging x back into the?
Where are we? You mean this number here?
No, on top, on the very top. When you're doing the concentrations.
Yeah, in other words, here's when I solved, I got x, right? And then I said, potassium is 2x, so I multiplied this by 2.
Okay.
Our zinc was 3x, I multiplied by 3. I did that on my calculator so I wouldn't multiply wrong. 2 I can usually manage, but man, I used to be able to do 10 minutes. I can still do 10 minutes. The other numbers, 7 or 8, I have to use the calculator. Yes?
Okay, so this right here is just finding it at a particular.
Yeah, I
meter.
just,
Okay,
in other words,
all right.
this one, the problem we originally did, I gave you the K, that was the one that was on the web page. I asked for the concentrations. Then I said the other type of problem we have along this lines, I can give you the concentration of something and ask you for KSP. And basically all I'm saying is, we would still set it up the same way, right? Except now if I told you potassium, and I gave you the molarity of potassium directly, you know that's 2x, so you get x, then you plug it in, raise it to the 7th power, times 432. If I gave you the number of grams in a liter, you have to remember molar solubility, you have to convert it to moles per liter.